All right, so moving into lecture 8 now that we've covered most everything about single system designs and measurement, let's get into more of analysis and what we can do with SingWin. So before we get into analysis, we also have to talk a little bit more about assumptions underlying our statistical analysis. So that's basically what today is going to be about. So back to our big picture, we've covered the goals, measurements, and evaluation design. But the first step of analysis is making sure that our statistical assumptions have been met. And I know that this may seem really scary to you, but with SingWin it's super easy. It's just a couple of clicks, so pretty basic stuff. So our very first assumption is normal distribution. So hopefully you remember some of this from 662 or a different course that you've taken. But a lot of people have talked about skewness or skewing data as in terms of contaminating things, and that's not what we're talking about with skewed data. When we want something that's normally distributed, it's going to have this nice little bell shape to it. So all behaviors are theorized to fall within this normal distribution. We can say through scientific methods or statistical methods, what would be the percentages of people that be expected to fall within 1 standard deviation, 2 standard deviations, or 3 standard deviations from the mean, which is right the middle score. But if we have something that's really skewed like this, where there's a few people who are outliers, then we would have issues with the assumption of normal distribution being violated. So here's another YouTube clip that I'd like for you to watch. I'm not going to post it within this video, but it's a video about normal distribution and behaviors that fall within the normal distribution. So please watch this YouTube video, and I think it'll give you a little bit more context. So let's just do a visual analysis of normal distribution. So for these groups, we've got one group of cocaine-dependent users who are receiving a normal medication, and a second group of cocaine dependence users who are receiving a placebo. And so in this graph here, you can see this looks pretty normally distributed, right? So number of individuals 0 through 60, number of days abstinent. There are a couple people it looks like who are up to 140 days abstinent, a couple people who could only stay a few days abstinent, but the vast majority of people kind of fall into this nice little bell, 60, 70, 80 days abstinent. So this looks like it's normally distributed to me. It's not perfectly normal, but looks really, really bell-shaped to me. But what about this one? This one doesn't really look too normally distributed to me. And this one is number of participants on the y-axis and frequency of on-the-job drinking on the x-axis. Here we can see that people who are frequency of drinking on the job, looks like about 50 people, or maybe 49 people said that they had 2 drinks while on the job. It looks like only about 6 people had 4 drinks on the job. And looking at 8 drinks on the job, maybe it was only about 2 or 3 people. So this is really, really positively skewed because there's a few people on the high end that are really pulling out the distribution. But what else do you notice about this graph? There's no people that are in the 0 category. So the vast majority of workers would fall into the 0 category. I know that I can't drink on the job. Most of you guys can't drink on the job unless you're working at a bar or something like that to get through school, which in that case I'm kind of jealous of you. But you can see that there's nobody here who's 0. So if there were people who were included in 0, then this would be really positively skewed because the vast majority of people would fall into the 0 category, and there'd be a handful of people that were in the 8 category. So this doesn't mean that we couldn't analyze this data, or we couldn't do anything with it statistically. It would just mean that we'd have to make certain modifications. All right, so another assumption that we have to meet is independence, or independence of observations, which essentially means that one observation isn't affecting the other. So an example of this, I don't know if you've seen the Dallas Buyers Club. I can't find a clip on YouTube. Maybe you've seen it, maybe you haven't, but there is a good scene from the movie where people found out that there's a treatment for HIV. This is back in the 80s. And everybody knew that they were either in a treatment group or a placebo group, but nobody knew which group that they were in. But everybody wanted some of the treatment, right? So what people in the study did was just mix up their pills so that everybody in both groups would be receiving at least 1/2 of the treatment. So this would mean that the observations were dependent because everybody was getting some treatment, and it wasn't really a true placebo versus treatment group, right? Because there was the overlap because they were mixing pills. So that would be an example where observations were dependent. They weren't independent groups who were being separately measured. So in this case, dependence is when one observation can be predicted from another observation. This can also be called autocorrelation, and this is going to be one of the first assumptions that you're going to be testing for with your paper. If your data is autocorrelated, then adjacent observations within the series of observations are impacting each other. So this is a really strong example of autocorrelation. And this is an example, I think, from previous semesters, number of unhealthy meals. So number of unhealthy meals, it looks like day 1 is 3, day 2 is 1, day 3 is 3, day 4 is 1. So it's got this really obvious zigzag to it, right? And in this scenario, there wasn't anything to do with the intervention. It was really just the fact that they were working from home one day and then they were on the road the next day. So it wasn't really anything to do with the intervention, but more of the fact that they were at work one day and the other day that they were at home. So if they're on the road, they're eating less healthy meals, obviously. But what would you do with data like this? Because if you're going to start an intervention phase, this autocorrelation would cause a lot of problems, because you might be led to believe that there was something to do with your intervention, but it was really just the fact that they're at work. And your statistics are just not going to run. You're going to have all kinds of issues. If anybody knows anything about autocorrelation and sees this, they're going to really question your results. So what can you do here? If your data is autocorrelated, you can do a transformation like a moving average. So a moving average transformation calculates the mean of adjacent pairs of data. So as opposed to that last slide where I showed you 1, 3, 1, 3, you would just be taking a 2 as their moving average for all those times. And then that way you can take their average baseline and compare it to their average intervention. And then we don't have any issues with independence of observation. So this is a really similar example. And here we've got number of child outbursts. So you can see that there's almost this perfectly predictable pattern here of up and down, up and down, and up and down. But in this scenario, the child was having outbursts whenever they were at their dad's house, but whenever they're at their grandparents' house, they weren't having outbursts. So in here, it would be the same thing, where the researcher would be led to believe that there was something about their baseline or something about their intervention phase that was leading the child to have a certain number of outbursts, or more or less compared to the baseline. That had something to do with their intervention, but it was really just the fact that they were going to their grandparents' house and they're having less outbursts there. So this is the exact same data, but using the moving average transformation. So here you can see that there's this nice flat line, and we can compare their average baseline outbursts to their average intervention outbursts. And so this is the first assumption that you're going to need to test for with your data, and we're going to do it with the Singwin activity. So this R sub F2 is the correlation or autocorrelation coefficient, and this T sub F2 is the test of statistical significance. So if this T sub F2 is below 0.05, the level of statistical significance for autocorrelation, then we need to do the moving transformation. So again, Singwin is going to give this statistic to us, and I'll show you in a different video. But if it's below 0.05, then we need to do a moving transformation because your data is autocorrelated.